Okay, so happy to have Yixian Wu speak about splitting formula of punctured Gromov-Witten.
Yeah, thanks, Bern, for introducing me, and thanks the organizers for inviting me. And today I'm going to talk about a splitting formula of punctured Gromov-Witten invariants. And actually, like my true topic is about a lot of things of punctured Gromov-Witten invariants, not only a splitting formula. And I hope like in the morning, Bern to kind of like motivate the like a little bit about the punctured Gromov-Witten invariants. And oh, okay, yeah. So I hope like in the morning that we're a little bit motivated to learn about punctured Gromov-Witten invariants. And today's like talk, it's gonna be a kind of like easy approachable talk, and I hope to talk introduce you to logarithmic geometry, logarithmic Gromov-Witten invariants, and I want to show you that this is actually a very nice object to work with, and it's very like friendly. So first, this is a picture that I always in mind when I think about the punctured Gromov-Witten invariants, because for Gromov-Witten invariants, we care about the maps from the curves to like a target. And for the punctured ones, I always think of it as a part of a nodal curve, which there exists another curve over here, and we are considering about the maps of such curves into our target space. Okay, so a lot of like case where so suppose we have a curve like A1 and we have a family of varieties, and assume that the central like the general fiber of this variety this family is smooth and the central fiber is a normal crossing variety. So the question I'm trying to like study today is how do we use the Gromov-Witten invariants on the central fiber to study those on the general fiber, because we know the invariants are deformation invariant. And so the question has two parts. The first part is what is the correct definition of invariance on a singular variety, and second one is can we reconstruct the invariance on the central fiber from the invariance on each component. Okay. So the classical story of this goes back to like 10 years or more than 10 years ago, where for the case where the central fiber contains two components glued along a smooth divisor, this is called the relative Gromov-Witten theory. And on the symplectic side, it is done by like Parker and Li Ruan. And for the algebraic geometry approach, it is done by Jun Li. And the way they do it is that they try to fill in the central, like replace the central fiber, the central target with a universal expanded degeneration. And we study the relative maps to that target, like that intersect with the smooth divisor transversally. And from there, we construct the relative theory of x1, comma d and x2, comma d. And there exists a degeneration formula that help us to reconstruct the invariance on the central fiber from each component. Okay, so an observation by
sorry, so this x in the formula is this x0?
Oh, yes. Yeah, thanks for, yeah, this is x0. Okay. Yeah, so an observation by Bernd is that in order to generalize this picture to normal crossing variety, that we probably need like some new technique, and the logarithmic geometry actually provides a very powerful framework to study such schemes with mild singularity, like toric singularities and the maps between them. And it has the advantage that a lot of like objects in the log category, like the way after we construct it, it's already like compact. So we don't need to worry about the compactification. Like for the moduli space of log smooth curves, they are already like compact. And yeah, so here is a brief history of the development of the logarithmic Gromov-Witten theory, where like it started like 10 years ago by a group of like Abramovich-Chen, Kim, and Gross and Siebert, where they developed the logarithmic Gromov-Witten theory. And the answer for the first question is finished in the paper by Abramovich-Chen-Gross and Siebert, where they proposed a decomposition theorem for like the logarithmic Gromov-Witten invariants. And Drew Ragnathan used the original like idea of expanded degeneration to study Gromov-Witten invariants, and later to address the second question, where we want to reconstruct the invariants on the central fiber from each component. The punctured Gromov-Witten theory is proposed like 2 years ago, a year ago. So the key facts I want to tell you today is that first, the invariance is deformation invariant on the logarithmic Gromov-Witten invariance. And the second one is we can reconstruct the invariance on the central fiber by a process called the logarithmic gluing, which is a fiber diagram in the category of some nice logarithmic category. And with the assumption of your gluing strata being a toric variety together with compatible toric log structure, there exists a numerical splitting formula, which is the thing I proposed in the title. Okay. Yeah, so let me go through some like basic construction of what is this log scheme. So a logarithmic scheme is a scheme together with a sheaf of monoids m of x and a morphism of sheaf from this mx to the structure sheaf, such that all the invertible functions are like the inverse image of the invertible functions are isomorphic to the sheaf of the invertible functions. And a key fact of log schemes is that there exists a smoothness like definition, and the log smooth is something like locally toric. And so here is a very first example of a log smooth object, which is the log smooth curve. And so I mentioned the Cato's classification of the log smooth curves. And when a log smooth curve are basically contains, it's a nodal curve together with marked points. So if we look at this example, that it's a curve, it's a genus 2 curve, and it has 2 components of a genus 2 curve and a rational curve. And we can have like marked points on the smooth part of the curve, such that the log structure is defined by some special part n here, which we can feel it as the marking at that point. And there exists another part which comes from the log structure of the generic like point of this component. And there are also the log structure associated to the nodal point, where here this will be like of the form where Q is the generic point, the log structure on the generic point, and we have such form. And we know for the nodal point, the ring of functions locally looks like kxy mod xy. So the log structure basically like remember something of this order, like it's something associated to this x to the a minus times y to the b. And so I always think of this nodal curve, like the log structure of it, as something, it remembers something related to the ambient space of this curve that lies in. And so from this description, we can feel it as like this kxy mod xy lies in a family of curves, where this in this definition of the nodal point, there exists a map from this n to q, and this thing tells us the deformation parameter of this family of the ambient space. And here this map, like n to n square, is always 1. The diagonal map 1 maps to 1 1.
Sorry, what is this q?
Yeah, so yes, it's a good question, and thanks for asking. So Q is the log structure on the curve of the generic point of the curve that, and we modeled by the invertible functions on it. So there exists so suppose this is a curve that maps to okay, so I lied a little bit. So I am thinking of this nodal curve as a smooth over some point with some log structure over Q. And if we look at the log structure on this nodal curve, it's gonna be, it will have a classification where over all the general point over here, it will have a log structure coming from this Q, for all the smooth point. And for the special point, like the nodal point, it will have log structure of this form, and the mark point will have another piece that comes from this and over here. Yeah, so Q will be the, yeah, Q, this will be Q. The thing over here. So it's the log structure coming from the generic.
So there is this monoid, the sheaf of monoids. I don't understand what is the sheaf of monoids.
Yeah, okay. So here, so let me add another page over here, and suppose yeah, so let us look at like the example that we had before. And I am saying this is like over a point, and together with some Q, and Q is a monoid over here, and it defines like a sheaf of monoids, which is basically, because this is spec K, so sorry, I am, yeah, so for this point, I give it a sheaf of monoids, which has this form, where like my map from alpha from M point to O point, which is just K over here, sends Q to sends all non-zero element inside Q to 0, and sends 0 to 1 over here. And then for all the nodal, like smooth nodal curves, there exists a log structure on my curve. This curve contains two components, C1 and C2. Right, and I can, for any like generic point for C1, I can associate with similarly like a sheaf of monoids with something like the O of C and O of C cross, where I do it similarly. I send all the non-zero elements to 0 inside O of C, and the 0 element to 1. And besides for the generic points of the component, I will have a special point over here where this has like more interesting log structure, where the log structure over here locally looks like Q direct sum together with N, and like the OCX and OCX cross, where the chart I told you that sends Q direct sum N to like
There's something wrong. You don't want to push off, right? It's just Q direct sum cross.
I'm sorry.
It's just Q direct sum cross. In MC.
Oh, but it says, wait, you mean like this?
The direct sum, you wrote direct sum over OC.
Yes. I want it to be like
you can write each section at the generic point uniquely as an element of Q to chart and then the variable function. Right?
Yeah. Oh, okay. I see what you,
Something with K down there. No, don't. What's the map from OC to that doesn't make sense, right?
You mean oh yeah, sorry. Yeah.
Yeah. I think
Yeah. I got like, yeah, there's no map from there. Yeah.
K down there.
Sorry. Yeah, I messed up with the chart, which is from Q to OC. OC. Okay. Yeah. Yeah, so here for each marked point, like there is an additional piece of this N which serves as a marking, and this, yeah, and here like this one is gonna send to T, and this Q, if it's non-zero, then it still sends to 0 inside this case. And similarly for nodal point, we have the description like this. So yeah, so that was the like a first example of a log smooth curve, and a second example which I find kind of useful to think like what a log structure gives me is called like Deligne-Fontaine log structure. Suppose I have a global chart which has the form like n to the r maps to this, and the push out of this chart gives me the log structure on my x, and this information is equivalent to I choose r line bundles on x together with a section for each line bundles. So yeah, so this is another example of the log structure, and the third example I'm gonna tell you is that's the case that happens a lot in application, which is a pair x, comma d, with d maybe a normal crossing divisor here, and we can define a divisorial log structure on it by we take the ring of functions such that it only has poles along d. Yeah, and so log Gromov-Witten invariants study the log stable maps from log smooth curves to the log schemes. And for like the stability over here is the same as the stability of the underlying maps. Okay. So there exists a hidden tropical picture for the log geometry, which later comes out is very useful when we do the application. And so the tropicalization of a log scheme is obtained by gluing the dual cones of this ghost sheaf for each geometric point, where this sheaf is we quotient out by the invertible function, the sheaf of the invertible functions. And let us look at the example that I was talking about, where here I actually take that Q that we appeared before to be N. And so this is the tropicalization of a curve where if we look at it, it's like the dual graph of this curve where each vertex associated to each component, a nodal point is associated to an interval over here, and a marked point, we can associate a marked point to an infinite lag over here. And so, and like in this picture, the tropicalization of pairs X and D are basically the cone over the dual intersection complex of this normal crossing divisor D. So the dual intersection complex is a triangle, and we're taking the cone over that triangle, and we get like 3 two-dimensional cones gluing together. Yeah, and the contact orders that we like talked about in the morning are defined by if we have so tropicalization is functorial, and for the tropicalization of the maps, we can associate like a map of the cone complexes, and this cone the map remembers some combinatorial information, including dual graph, the contact orders, and the image cones of each nodal point or like the marked points. And the contact order here are defined by taking the dual of the like the sheaf of the monoids, and we project it to the factor that we add for each marked point. So, and yeah, so tropically it corresponds to like a ray inside the dual cone, which is the tropical picture that we're adding over here. So here is an example where we map this genus 1 component onto this curve, and we contract this like rational curve with 3 like special points to this point, and topically it corresponds to we send this vertex to the strata associated to like this this component of D, and we map and the 3 rays over here remembers the contact orders of each like marked points, and the direction of the orange curve over here remembers the contact order associated to the nodal points. So there exists so for each like I mean map over here. So each map C to X over a point, there exists a universal log structure called basic or minimal log structure. And this universal log structure is actually determined by the tropical moduli space of the type associated to this curve. So to be more concrete, the dual cone of this, so it's the tropicalization of this point is the cone parametrizing all the type tropical maps with the same type. So yeah, so the good thing about this is that like the log structure and the tropical geometry behind this is actually kind of like a part that we cannot see on the schematic side, but it tells you like remembers like the underlying like the deformation in like the information which we encoded inside this log structure. Okay, so the answer for the first question is positive. Log Gromov-Witten theory is deformation invariant, and we can have a decomposition theorem where for the moduli space to the central fiber, we can write it in terms of the types, which are the rigid tropical types, which are the types with the minimal like tropical moduli space. So here is an example. So suppose we are considering a degeneration of cubic surface defined by like a degree 3 function f3 plus x1, x2, x0 equals 0. And we consider the degeneration defined by this equation, and we want it to be like a normal crossing degeneration. So we need to blow up 9 ordinary double points, and the central fiber now becomes H1, H2, H3 with some like blow up, and it becomes normal crossing. And we give like the family a divisorial log structure coming from the central fiber, and we get a log smooth family over A1. And here is an example of what a rigid tropical type would look like. So consider the tropical type with the curve having 4 components, C1, C2, C3, and C4, where C1, C2, C3 are mapped to each component of the central fiber, and we contract C4. And so for this, tropically, it will correspond to 3 vertex over here and another vertex in the middle. However, like since we contracted this component C4, there exists like the contact order associated to it should satisfy like the balancing condition, and the balancing condition fixed this curve C4 to lie in the middle of this triangle, which is the dual intersection complex of the central fiber. So yeah, so which means we cannot move this point around, and this is an example of the rigid tropical type. So I will briefly like sketch the idea of the proof of the first like theorem, like the decomposition formula is that we have this moduli space of maps, and it exists a perfect obstruction theory over a log smooth space, which is called this frac M like X, which I will tell you in the next page what this means. And but locally, this is very nice since it admits like a toric model and with the toric structure determined by the tropical moduli space. So this is a very like nice object. This is like pure dimensional, and like the toric geometry tells us how do we get the central fiber by like some toric manipulation. Yeah, so here I'm gonna introduce an object called Artin fan, which is an algebraic version of tropicalization, which is a very like important tool for us to like study the study the like the log Gromov-Witten invariants. And this is obtained by, so remember like the tropicalization, we are taking the dual cones and we glue them together. And here we are taking the an Artin cone, which is defined by like a aventoric variety modeled by its maximal torus. And we glue them together in the similar like fashion, and we get a stack, which is called Artin stack. And the reason that this is something very the reason I call it this is an algebraic version of tropicalization is because if we look at like a log scheme, and the home of the log schemes to this object Artin fan is in a bijection with the home of the tropicalization of it, with the tropicalization of the Artin fan. And this is a very nice object because it's log Ital over a point. And if we look at all the curves to it, like it is unobstructed over a point, and it is log smooth with log structure determined by the tropical moduli space. And we have a perfect obstruction theory of the moduli space over this moduli space of maps to the Artin fan. Yeah, so now I am gonna tell you something about the second question, where we finally we're gonna do the splitting, and we are gonna consider like what it will happen if we how do we like think to get the invariant on the central fiber from the invariant on each component. And so we start with a splitting action on the curve, and yeah, and the problem that occurs is that when we split along the nodes, the subcurve of it are no longer log smooth. And if we look at like the log structure on the nodal points, it has something like it has the form of this like this push out. And when we think about the contact order of it, it will maps to some like QAB to A minus B, which is possible to be a negative number. And which means if we look at this curve as implicitly thinking of it embedded inside the nodal curve, like the negative contact order like naturally occurs. And tropically, if we look at the dual picture, the punctured like points will correspond to the legs with finite length. Let's suppose we look at it, this C2, if we split along this edge, we know that this leg can only extend to here, that it cannot go beyond this. So it will correspond to like a finite leg instead of the marked points corresponds to like the infinite legs. So a punctured curve is a log smooth curve together with another like a puncturing structure, where this here P we select out a bunch of like marked points, and we allow the negative elements coming from that marked points. And yeah, and in addition to that, since we are allowing like the negative orders over here, which means suppose something is negative over here, when we map it to like the structure sheet, that thing must map to 0. Otherwise we cannot take like like the inverse of that function. If it's it's like if we are looking at k of t, if we maps to 1 to t, we do not have the image of like t to the -1 inside this k of t. So that, and if something like this happens, then we must map that element to 0 to fix this problem. Yeah, so a punctured map is the log map from a punctured curve to a log scheme. And the requirement over here tells you, if you are looking at the punctured map, the negative contact order forces the components of C lies in certain strata of X. And here is an example of the thing I just claimed. So let's consider a punctured map from a curve to XD in the following way, where I have a rational curve with 1 punctured points, and I fix my contact order to have something like 1 - 2 over here, which means it goes this direction. And yeah, and the condition that we had before forces this curve to lies in the component associated to this to this strata, which forces the component to lies in here. That it's so tropically, if we look at this, if the component lies in this strata, we cannot add a lag in this direction at all, which geometrically means the condition for does not allow the curve to map to the strata of this D, like this component of D. Yeah, so so there exists a natural finite representable splitting morphism associated to the splitting process that we just talked about, and virtually there exists a Cartesian diagram in the category of fine saturated log stacks, and with a little bit modification of the log structure on our moduli space, we can define a log maps, log evaluation maps, and we can reconstruct the virtual fundamental class of the glued space by taking a logarithmic fiber product. And yeah, and the thing about logarithmic fiber product is it's the good part and also the bad part. Like the good part is this is more close to like a toric fiber product. And the bad part is this is not a schematic fiber product anymore, and we would need to take some saturation, and it will be like the space we get is like a close immersion together with some like several like components of the same one. So it's so it's more complicated. And but for the case where your gluing strata are toric varieties, this is actually pretty nice, and such diagram locally looks like a toric fiber product. So so let me give an example to try to show like why logarithmic fiber product is different from a schematic fiber product by just look at the easiest example of the fiber product of points. So if we glue 2 points along a point, that we know for schematic fiber product is always a point. But if we look at like the log fiber product, it can be something non-trivial, which here we get like 2 disjoint, like the disjoint union of 2 points. And the reason behind this is if we look at, so here we are mapping a point with a non-trivial log structure coming from a monad N to like another coming from monad N, where the monad morphism sends 1 to 2 for both maps. And the naive fiber diagram that we take along for the log structure is like n squared mod 2a equals 2b, which this is not a saturated monoid, and taking the saturation amounts to that we require this this component to separate into two components. And geometrically, we can view it as like embed this log points inside a curve. And this is inside like A1, and we take the fiber diagram of the A1 with two like maps as T maps to T squared, we will get something like KXY mod dot X squared equals Y squared, which is a double point. And yeah, and taking this saturation that we would normalize this this like two double curves, and we would take out the two components. That's the reason when we take this saturated log fiber product, we get two components of the. Yeah, but on the other hand, logarithmic fiber product of toric varieties is very close to the like the fiber product of the associate fans. So here is a very useful lemma is that the fine saturated log fiber product of toric varieties is a disjoint union of toric varieties whose associate fan structure is obtained by we take the associate fan fiber product of the toric varieties we start with. And this multiplicity over here comes from the torsion part of the torsion part of the fiber sum of the dual of the associate like the groups, and this multiplicity can be computed using a lattice index. Yeah. So yeah, so now we're ready to study the gluing process because we know like we know a little bit about the logarithmic fiber product now. And the key fact is that the evaluation map from the actually it's the frag M space that I told you, but here I treated a little bit by writing like the virtual class of the space maps to X is idealized log smooth, where idealized log smooth means locally it is a closed immersion of toric strata and together with a toric morphism. And we have very good control over how this like local toric model looks like because like we know the log structure on this toric stratas coming from the tropical moduli space. And the ideal structure of this comes from like three parts, where one part is we fix the tropical type, and we have the puncturing restriction that we had before, and there is some evaluation like thing when we take the saturation, and there are some evaluation marking that it will like, yeah, which basically means that we have a very like good idea of how this ideal structure would look like. And yeah, and the log structure on those space are controlled by the tropical moduli space, where these tropical evaluation maps are determined by the evaluation cone, which is basically the tropical moduli space together. We add another marking for each edge and leg that we evaluate at. And yeah. Yeah, so so before I told you for the gluing diagram, we know locally they all look like toric morphisms, maybe with some idealized structure. And a very classical result in the intersection theory of toric varieties is called Fulton-Sturmfels Formula, where it tells us how we study the push forward of the toric morphisms of the fundamental class under the toric, like the proper toric morphisms. So suppose we have a toric variety with fan sigma x and x, and we want to study the diagonal map of it, and a vector inside the lattice of x cross x defines a GM action on x cross x. And geometrically, if we try to take the limit under this GM action, where t goes to 0, we can get a torus invariant subscheme that is rational equivalent to the image of the diagonal map. And there exists a like a combinatorial manipulation called fan displacement rule tells us exactly that what this limit is going to be, which is and the classical lemma of Fulton-Sturmfels tells us in the child group that the push forward of X has this explicit form in terms of a strata, the two stratas of the product of the stratas of the toric varieties. And these we can read off these cones by a dimension requirement, and we wanted to intersect transverse like at exact point after we displace it, and the multiplicity is obtained by a lattice index. So here is an example which is kind of similar to the one, it's the same as the one that Bernd mentioned in the morning, is that suppose we consider P1 maps to P1 cross P1, and the fan map is we maps like a A1 diagonally onto A1 cross A1, and we pick a generic displacement vector, we move it like along that vector, and we can read off like the strata that will contribute as the limit over here, where we take the points that the intersection points of this with these two rays, and we can get like the push forward of P1 equals infinity times P1 plus P1 times 0 by this fan displacement rule. Yeah, and the thing like implicitly behind this is that such displacement vector defines a deformation of our image such that it is compatible with the log structure. And that's pretty nice for the toric varieties, and that's not that's kind of hard to find in general. And I think that's part of the reason that this like the splitting formula requires the toric assumption. And so with the same like spirit, now we are considering like a fiber diagram of this form, and we're trying to find out the push forward of the virtual fundamental class upstairs. And so we do the similar thing. We can take a generic displacement vector inside this C cross C, and as I like told you already, like the fiber diagram of the toric varieties in the log category can be studied using the fiber diagram of the fans. So here it is enough for us to take a generic displacement vector on like on the lower part inside NZ cross NZ, and we it can be lifted into a GM action on the upstairs. And if we take the limit of t goes to 0, it gives we can read off like the strata upstairs of how we get like the like a rational like equivalent class. Okay. Yeah, so here is the theorem that there exists a virtual push forward under this, where we obtain this strata in the similar spirit of the Fulton-Sturmfels formula. And the multiplicity is again obtained by like a lattice index. And and numerically we can pair it with like we can pair it with the like the cohomology class, and we can get a numerical splitting formula of the cycle version. So here is an example of the situation that we considered before, where we map 4 components like where we talk about the rigid type, that I mapped 3 components to like the 3 components of the central fiber, and I contracted 1 component. So if I fix a displacement vector V over here, that basically I am changing like the matching condition, and now the matched ones will be like 2 components maps to the general strata and I degenerate one of the component, either C1, C2, or C3 into one of the deeper strata. And for C4, it's already contracted, so it's already in the deepest strata. So we cannot like degenerate it more. And yeah, and these three types are the types that match after the displacement. And these are the types that give us the numerical information of the, of the invariance. And geometrically, it corresponds to one of the components C3 degenerate into this strata. So here C2 degenerate and here C1 degenerate into the strata. Okay, so one of the application of this is another proof of the Mikhokhin and Gross-Siebert tropical correspondence theorem, where because like in this so in this setting, we would require the gluing strata to be toric varieties and like to be able to embed it in some toric varieties. And the natural playground is suppose our target themselves are toric varieties. And these are very closely related to the tropical curve counting problem. And so suppose that our target itself is toric variety, and we want to study the invariance where like we require some marked points pass through the closure of the subtorus defined by some affine subspace, like the linear subspace of your fan of X, and how many like m marked rational points are there inside this toric varieties. And we can restate the question by saying that I am considering a type with graph G containing a genus 0 vertex and n contracted legs, and what is the degree of the virtual fundamental class of this space in terms like which I defined it using this fiber diagram. And we can do the similar thing. And here, like the generic displacement vector also like occurs inside like the original paper by Yixian and Siebert that we perturbed it in a general way such that there exists only finite collection of the tropical types that will contribute, and the splitting formula gives you for each type what's the multiplicity contribution of that tropical curve counting. Yeah, and another example is if we are thinking of a higher genus case. And so suppose we have a genus 1 curve with following type, and I want to, and I require like the contact order of them to have the same like direction. And if I split along both edges, but I choose different displacement vector of it, we can see like immediately that there's no way that they can still be matched if I choose the different displacement factor. So it can be read like directly that we know that such type does not contribute to the invariance. And I think as an application, it will help us to like consider the higher genus like tropical curve counting problems. Yeah, and there is a small remark for the case that what if the gluing strata is not toric and the displacement, so as I told you, like the displacement factor give us like a rational equivalence like class which is compatible to the log structure. So suppose we have a nice situation where you still can find like a family of maps over A1 such that on the generic point it's isomorphic to your diagonal map, but also it's compatible with the log structure. And in this case, the same idea can go through, and we can still come up with some good we can still pick some good like strata inside your glued space to provide like the rational equivalent class. But but that's the only like other like generalization I can think of right now. And for a more general case, that we would probably like go to the like, yeah, we would, yeah, it's not definitely not enough to consider in the like the child group or the child homology, and we would need probably like more like a better idea to how to solve that questions. And this is, yeah, not like, I'm not sure how to do that right now. Yeah, so that's the end of my talk, and thank you for your attention.
Yeah, so you can generalize this to the orbital set.
To the orbital setting, I think it is, oh, it is like okay to generalize. Yeah, let me think. Okay, but yeah, I think probably Bernd is better at understanding this for the punctured invariants on the for orbital. I guess like the,
Any other questions? Yes,